Good morning. My name is Adan Hernandez,
And I'm Kassandra Forrest.
and we are Team Horizon. We are presenting our CPU called New Horizon, which is a 32-bit Mips processor.
We decided to use the name New Horizon in honor of the satellite NASA sent to Pluto, and decided to commemorate their accomplishment as the name of Horizon.
So today's objectives are a brief history of Mips, architecture of the CPU, our data types, our addressing modes, our block diagrams, enhancements, and we will finalize with the Q&A session. Mips is a reduced instruction set computing CPU design. Arose from Dr. John Hennessy's work on computer architecture at Stanford University in the early 1980s.
In the diagram, we're showing the changes that happen to the Mips processor as it went on, as far as register count, cache, and model, and clock for each update of the model.
We are using a Harvard memory architecture and organization. This New Horizon processor uses a Harvard memory architecture, which allows two memories. One is running the execution of the code, while the other one is transferring data at the same time, concurrent, using separate buses, data buses. Our address space in New Horizon is a 32-bit address space with address starting at hex value 000 to 3FF for running code execution simulations. We are using Big Endian. All instructions and data memory locations are byte addressable, where at each memory address, a byte is held. In this memory architecture, all 32-bit data and 32-bit data instructions are saved into 4 consecutive memory locations and therefore are word aligned. Our machine register set are 32-bit registers that are 32 bits wide. There are 32-bit wide registers available to the user on the New Horizons processor. Only register 0 cannot be written to. Our flag status. The following status flags are C, V, N, and Z. C is for carry, which indicates if the calculated result of the arithmetic or logical operation causes a carry out to occur. Overflow indicates if the result of an arithmetic operation does not fit within the 32-bit register data size. Negative indicates if the result of an arithmetic or logic operation produced a negative value, or if the value passed through the arithmetic logic unit is a negative number. And 0 indicates if the result of an arithmetic or logical operation produced a 0 value, or if the value has passed through the arithmetic logic unit was a value of 0. Our data types, we have signed and unsigned, with a maximum value of -2 billion to +2 billion. Unsigned integers are a maximum value of 0 to 4 billion. Our instruction set, all R-type instructions will use the following formats as follows. Our opcode field is a 6-bit value that will always be 00 for R-type instructions. These are stored at bit locations 31 to 26. RS will be a 5-bit value that specifies the first source register address. These are stored at bit locations 25 to 21. RT is a 5-bit value that specifies the destination register address. These are stored at bit locations 15 to 11. And the shift amount, which is a 5-bit value that specifies the amount of times to shift the register selected in the RT field. This field value is only used in shift instructions. These are stored at bit locations 10 to 6. Our function field, which is here, is a 6-bit value that is the opcode for R-type instructions. This location specifies the instruction to be used. Location bits are 5 to 0. Our I-type instructions will use this format. where our opcode is the same as the R instruction. The bit locations are 31 to 26. We don't have a destination register. We have an RS, a 6-bit value that specifies an I-type instruction to be performed. These are stored at bit locations 31 to 26. The RT is a 5-bit value that specifies the destination register address. These are stored at bit locations 20 to 16. Our immediate field is a 6-bit value that is used for both arithmetic and logic operations. These are used as sign, offset, and load and store operations. All J-type instructions will use the following format as presented. We have an opcode field, which is a 6-bit value that specifies a J-type instruction to be performed. These are stored at locations 31 to 26. Our address field, which is 26 bits wide, is a value that specifies the destination absolute address for PC to jump to. This is stored at locations 25 to 0.
And finally, we have our enhanced instruction formats. We have 3 different formats for the type of instructions we're doing, and the first one is the jump enhanced instruction format. The opcode is always set to a value of hex 0x1f with bit fields 25 to 21 defining which instruction exactly is going to be performed. There's 21-bit immediate value. Oh, I'm sorry, that is a mistake. The 21-bit immediate value will be used in conjunction with the program counter to determine where in the program we're exactly going to jump to. The enhanced instructions jump if carry, jump if negative, jump if 0, and jump if overflow will be used. These are the constant values that can be used to select which type of jump you're performing. For our branch enhanced instruction format, again, we have used the enhanced keys as the opcode, and we are now using a 5-bit field to specify RT, which will be used in the branch instruction to determine if the branch will be performed or will not. The 16-bit opcode value will be used to branch to the selected address. The 2 types of branch enhanced instructions that are provided are branch of less than 0 and branch of greater than or equal to 0. And finally, we implemented the barrel shift right with rotate and barrel shift left with rotate. They, following the style of the enhanced key, the opcode is set to 0x hex 1f, a 5-bit function field, RT and RD amount, and a shift amount field. RT and shift amount will be used as operands into the instruction, and will have their value placed into the RD register. Bits 5 to 0 in this instruction are unused, and these are the available instructions for the barrel shift with rotate instruction format, barrel shift right with rotate, and barrel shift left with rotate. And now we will continue on to the addressing modes of our processor.
We have an immediate addressing mode, which is immediate addressing mode is when one of the operands itself, not the address of the operand, is being used in the instruction. Right here, we display a figure that shows that the immediate value is being used directly in an arithmetic operation, alongside the register contents of the register specified in the RT field, and having the product of this operation being stored in the register specified by the RT field. Next is register addressing mode. In register addressing mode, all operands and destination location are CPU registers. This figure shows that the register and registers specified by the RS and RT field are being used directly in an arithmetic or logical operation. The product of this operation is then stored in the register specified by the RD field. Third is our register indirect addressing mode. This addressing mode is also known as register deferred. This is a mode in which a register is holding the address of the operand. This addressing mode is typically used to access operands pointed to by base pointers that are stored in registers. In this figure, we are adding the value held in the register specified in the RS field and the sign extended value of the immediate field, and creating the effective address that we would use to locate that we will use to address a location in memory. The contents inside this memory location specified by the effective address are then to be loaded in the register specified by the RT field.
And you see inside the figure, we have a basic pseudo instruction format of how exactly the instruction will go through. And finally, we have PC relative addressing mode. This mode is using a data instruction memory location. It is specified as an also relative to the implemented PC. Typical uses of this mode are for branching or jumping from the current location in the program to a specified location in the instruction. So the immediate value alongside the program, the current value of program counter are used in conjunction to be loaded onto the PC register if and only if the branch formality is met. And here we have the branch address being the PC plus a sign extension immediate value with shifted to the left twice. Oh, and the PC will have that branch address loaded onto it if and only if RS is equal to R2. And that is the branch is equal to R3, R2, and R2 being the two registers that are being evaluated, and the label 1 being the immediate value that we'll use with the PC value. And now we will introduce our enhanced instructions. Here we have our jump of carry, a conditional jump that is dependent on a previous operation having produced a carry. If no carry was produced, there will be no jump will occur. On the next section of the slide, we show the basic control word used to perform the jump of carry state with the PCC, the current state of the flag, controlling should the PC be updated with the branch address or should the PC continue on to the next instruction. Here we have a pseudo example with assembly code showing how exactly this would work as a programmer's perspective. It would be the contents of R2 and R5 being added together to R4 and the contents of R4 being added with R0, which has a constant value of 0. So if you add any constant value with a value 0, you will just have 0 within it. So if the statement is true, the program counter will jump to the location of the lower label, which is at address 0x200, and proceed to perform these operations. That was my mistake. For jump if carry, as it goes down into the lower label, it will perform a subtraction between, an addition between R2 and R6, R2 being hex 0x000FFF and R6 equaling 0xFF05C. When you add these two numbers, a carry is produced, and it will jump back to the label of top, meaning that it will change the current value of the program counter to where the top label is. And the div instructions will never be performed because we never went to it. The jump of 0 follows almost the exact same logic, except the flags that are being checked now is a 0 state flag. And all the jumps, depending on the flags of ALU, all operate in the same amount of time. And here we have a pseudo example of jump if 0, where we are actually clearing R4 with R0, and since R4 no longer has any value, meaning that it has the constant value 0 in it, it will jump to the label, never performing the AND instruction. R5 and R0 ANDed, put into R4.
What in the Verilog that you've got up the top, what's the difference in the control words between the if and the else part? In other words, we're outputting these control words.
On the if if statement, these control bits on the side are the only ones actually being set on. If you look at the bottom section, none of these have any ones being included. Here, PC
So
select,
which bits in particular change?
PC select, PC load, and PC ink have
Okay.
changed on this one.
Great, thank you very much.
Jump if overflow is a conditional jump that is dependent on a previous operation having produced a full overflow. Again, they work, the jumps on the arithmetic flags perform exactly the same, except the only difference being what exact arithmetic flag is being checked. And jump if negative, finally, to wrap up the jump types, performs a jump if and only if the negative flag has occurred in the case where the value is less than 0. Finally, we're introducing our barrel shift right with rotate.
So right here, we have a barrel shift, rotate right. A shift with rotate to the right, and no bits are lost when rotating, compared to a shift right logical or a shift left logical. A 32-bit value can be shifted to the right with rotate for a maximum of 31 times in one instruction call.
The reason being for it being 31 times is that the shift amount field is used and it is a 5-bit value, so we can only shift to the maximum value that 5-bit field can hold.
The barrel shift rotate left is just the opposite of the right. So shift with rotate to the left, no bits are lost when rotating as well, and the 32-bit value can be shifted to the left with rotate for a maximum of 31 times in one instruction call.
As for the branching conditionally, we decided to do a branch if less than 0. A conditional branch is dependent on the contents of the CPU registers being evaluated. If the register is less than 0, then load the program counter with the specified branch address. In this example, R2 and R6 are added together. The most significant bit of R6 is set as a negative number, so when you add these two together, the value that you will produce is a negative value. So since the status flag previous to this was set as it being a negative value, which is less than 0, it will jump back to that location in the program counter specified by the immediate value, which is the top label. And for our second branch, we did branch it greater than or equal to 0. A conditional branch is dependent on the contents of the CPU register being evaluated. If this register is greater than or equal to 0, then load the program counter with a specified branch address. Here we attempted to perform the same branching to the same label on top, but since the value is actually a negative number, there is no way that it is greater than 0, so it will just fall through into the next instruction. And in an homage to our first assembly class, in having performed a no-op instruction as our very first instruction, we decided to include a no-op. A no operation occurs in the CPU for 3 consecutive clock periods. Our reasoning for adding this operation of doing nothing was for any timing constraints that the programmer might need, where they felt that they would need 3 consecutive clock periods or multiples of 3, that they're allowed to use this operation to use it. And if should they be a new time programmer, just like we were, where they would implement a busy wait loop, they can use this instruction and have nothing going on.
Are there any other MIPS instructions that actually do a no-op? That you could actually do a no-op? In other words, move a register to itself?
Yeah.
Copy a register to itself would do a no-op, right?
Yeah, that would be 4 clocks. So we just decided to keep it as 3.
3 clocks, okay.
And finally, we will look into the hardware implementation of this. This is a general block diagram of how the CPU, I/O memory, and data memory are connected. The CPU is sending control words signified by the orange arrows into the I/O memory and into the data memory. It's interacting with the data memory and the I/O memory. Data is being sent into data memory, and data is being sent into the I/O memory.
How come there's 2 red buses on the I/O memory?
believe one of the buses was set as interfacing with a different portion of the CPU, so we just had them to be
Like control
separate.
signals maybe?
Yeah.
Huh? Okay.
So now we'll look closer into what's inside of the CPU. Inside of the CPU, we have the control unit, instruction unit, and integer data path. For simulation purposes, our system clock was a 10 nanosecond clock, so 45 megahertz clock. And we have control words and a separate controller for the integer data path and another controller going to the instruction unit. Interrupts are allowed to be used on the control unit to signify that an interrupt instruction will occur. And interrupt technology is set out from the control unit. Since the CPU is connected to a data memory and an I/O memory, we have I/O memory and memory controls going out of the control unit. And I/O data and memory data are allowed to enter the integer data path.
Do they have separate paths into the data path?
Yeah, we created 2 separate paths into the data. To go inside and see exactly how our instruction unit is performing, we decided to show the overall schematic of how
Mm-hmm.
everything is operating. Here, the only thing that was different from the baseline that was added was the E enhanced address. So the PC select was increased to accommodate this new E address and is used in conjunction with the jump if carry and the new branch enhanced instructions.
Did you ever explain to us what the E address was?
Yeah,
Okay.
the enhanced address.
What was remind me again, what was the enhanced address?
The enhanced address is if it is a jump, it uses bits 2120 to jump to that location, and if it's a branch, it uses bits 15 0.
Thanks.
We have our PC register, which goes into our instruction memory and fetches the next instruction to be used. You can only fetch from the instruction memory if you select the chip select and IMRD. Though it has an input of IM write, there is no actual writing to the instruction memory. The instruction that was fetched is loaded onto the IR register if and only if the IR load has been asserted. And IR out will be the actual contents, the bits that make up the instruction. And the sign extension out is to be used with any branch or jumps that are to be performed. Now we'll look closer into what's inside of the integer data path. This is an overall schematic of what exactly is going on into the integer data path as to how or what was added to make our new Horizon processor work. We decided to add an extra address mux in front of the register file, specifying this as a stack pointer because for one of the baseline enhanced instructions is a red eye. We decided for the S address to have the value of the register as one of the constant values to be selected from the S address mux. Here our destination address, no modifications were performed on it. It still points to the stack pointer, to the return address, the T address, and the D address. You can see the logical flow of the register file into the RS and RT registers with the T mux in front of the RT register, specifying that you're allowed to choose data outside from the integer data path or within the register file.
Mm-hmm.
But a closer look at the ALU, you can see that the CV and Z flags, the CV and Z flags are only updated by the ALU module unit, in which holds our barrel shift right with rotate and our barrel shift left with rotate. One of our enhanced instructions required that the flags and the PC be saved onto the data memory.
Mm-hmm.
So the modifications of adding a PC register to hold the contents of the PC for 1 clock or 1 clock longer be saved onto a register, and the flag status be available as one of the options to be data out from the integer data path. a closer look of the interconnections of the register file. The register file is only allowed to have two register sources being read at one time. And our system file consistent use of being at the top, mandating how all timing within the module will perform. T address always has a T address of it being itself. Here we added on the ALU where the contents read from the register file are loaded onto the ALU and the function selected to perform are used. Shift amount won't be used if it's not a shift right, shift left, or shift left logical, or shift right logical. Back to the overall schematic, this just shows all components not interconnected. Depending on the operation being performed, the register is not attached to the ALU. Attached to the outputs from the ALU or the DN or PC register will be outputted by the integer data path as ALU out or D out. Going back to the top to where the integer data is actually implemented inside of the CPU. To the overall block diagram, which holds all of our components within it. To the end of our presentation.
Thank you very much.
Thank you.